In this video, we're going to learn how to visually represent the structure of hydrocarbons, as well as how the naming system for all organic molecules works, or at least the foundation behind it. Now, hydrocarbons, as you'll recall, are any element that contains only carbon and hydrogen within its structure, and consequently, the only major difference that hydrocarbons have, or that one hydrocarbon has compared to another hydrocarbon, is simply the number of carbon atoms that exist within the compound, and this is the most important characteristic to determine, because this is going to affect the prefix of the hydrocarbon's name. For example, if a hydrocarbon only has one carbon, we can identify that with the prefix meth. If it has two carbons, it would be represented with the prefix eth, 3 carbons represented by the prefix prop, 4 carbons, the prefix is but, and then from here, the prefixes are identical to the covalent naming system in terms of identifying how many atoms exist within a covalent compound. For example, the prefix for 5 is pent, the prefix for 6 is hex, 7 is hept, 8 is oct, 9 is non, and 10 is dec. And for practice, what I like to do in order to commit these prefixes to memory is see how fast I can repeatedly say them one after another. For example, meth, eth, prop, but, pent, hex, hept, oct, non, dec. If you think you can go faster, try meth, eth, prop, but, pent, hex, hept, oct, non, dec. If you think you can go faster, meth, eth, prop, but, pent, hex, hept, oct, non, dec. And anything faster than that becomes gibberish if I try to say that. Now, these are only the prefixes. The next characteristic that we need to identify are the types of bond that exist between one carbon and another carbon here. For example, if we look at all of the hydrocarbons below, we see that these hydrocarbons only contain single bonds between all of the carbon atoms. We don't see a single double bond or triple bond within these structures here. And these hydrocarbons are classified as alkane molecules. So an alkane is an example of a hydrocarbon like these that only contains single bonds within each of the carbons, or within each of the links between carbons. And as these are called alkanes, we give each of these the suffix ane. So for example, this hydrocarbon, we see 1, 2, 3, 4, 5, and we know the prefix for 5 is pent, and because it contains only single bonded carbons, this is what we would call pentane. If we name an easier one here, this one only has 3, we see the prefix for 3 carbons is not tri, it's actually prop, and therefore we would call this propane, which is indeed the gas that is found in barbecue tanks. This rather long one here has 1, 2, 3, 4, 5, 6, 7, 8, and we know the prefix is oct, and again, carbon to carbon single bonds implies that this is octane, and this is the principal hydrocarbon that exists in gasoline. Now, the rest of these, you can figure it out from yourself. It literally is as easy as counting carbons and simply looking at whether the hydrocarbon has only carbon-to-carbon single bonds. What is more interesting to experiment with is actually drawing hydrocarbons. So, we're going to practice drawing the full structure, which we actually see listed here, and then look at a way to speed up the process drastically. For example, the hydrocarbon ethane, we know that eth is the prefix for 2, so we are going to have 2 carbons that are single bonded like this. Now, we know that carbon can make 4 bonds, which means that each of these carbons is going to have a total of 4 bonds, and then because these are hydrocarbons, we simply attach hydrogens onto the carbon like this, and from this we can figure out the chemical formula for ethane, which is going to be C2H6. Now, that didn't take particularly long, but we can see as the number of carbons increases, for example, if we take a look at butane, but is the prefix that means 4, so we are going to have 1, 2, 3, 4 carbons that are all single bonded to each other, and then we're going to have to give each of those carbons 4 bonds like this, and here comes the rather frustrating part of actually drawing hydrogens to match all of those single bonds so that each carbon has a total of 4 bonds attached to it. Then if we write our chemical formula, butane has 4 carbons and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Now, for those that are wondering, God, there must be a faster way in order to draw these. In fact, there is, and I will show you. Everybody watch. Done. This structure here is a simplified way to represent ethane. Do we want to see that for butane? Here we go. Done. This is a simplified way to represent butane. So these structures here are what we call line structures, and if you do a Wikipedia search of pretty much every organic compound, this is the structural system that is used to represent organic compounds, as many of them get quite large and difficult to draw if we were to draw a full Lewis structure for them. So how do line structures work? Well, every time there is a bend in the lines, that is a carbon. I'll draw that better here. That is a carbon. So there's a carbon here and there's a carbon here. Every time there is an end to the line, that is also a carbon. So we can see 1, 2, 3, 4, 2 ends and 2 bends in the line like this. Now, the only bonds here that are explicitly written out are the carbon-to-carbon bonds that make up the backbone of this line structure here, and all of the bonds between carbon and hydrogen are not shown. For example, this carbon here has 1 bond to this carbon here, which means that it's missing 3 other bonds rather, 1, 2, 3, and now we can see that this carbon has 4 bonds in total, and each of those bonds that is not shown by the line structure is to a hydrogen. Now, these 2 carbons in the bends in the line structure, each of those has 2 other bonds that are going to the 2 adjacent carbon atoms, meaning that there are 2 bonds with hydrogen that are not shown like this. And then finally, this carbon on the end is like this carbon on the end. There are 1, 2, 3 bonds with hydrogen that are not shown. And if we make this slightly more complicated line structure and compare it to the full Lewis structure, we can see same number of carbons bonded together and same number of hydrogens. And that's why this is equal to this. Now, for an extreme example to show the difference between how long it takes to draw an actual line structure, we can try heptane. Hept is the prefix for 7, which means there are 1, 2, 3, 4, 5, 6, 7 carbons arranged like this, and we need to give each of those carbons 4 bonds, meaning that the carbons on the end have 3 hydrogens bonded to it like this, and the interior carbons inside the chain are going to have 2 hydrogens each, and you can see that this is a rather annoying pain to draw all of the hydrogens, but if we try drawing a line structure, 1, 2, 3, 4, 5, 6, 7. And just to count carbons, 1, 2, 3, 4, 5, 6, 7. Every time there is an end of the line or a bend in the line, that is a carbon, and all of the bonds that are not represented represent the bonds between carbon in the chain and hydrogen coming off of the side. Now, in order to practice your familiarity with naming simple straight chain hydrocarbons, see if you can use the numerical prefixes to name the 3 hydrocarbons below, as well as draw both the full structure and line structure of the remaining hydrocarbon here before the next video, where we will take a look at more complicated variations in hydrocarbon structure.